Go for
Yeah, it's setting up.
it.
Done. Just a second. I'll just mute the live stream so that it's not feeding back continuously. And I'll share. Okay, that's great. It's muted by default. I'll share the link so that you can then share it on Typora. Oh, sorry, on Persona.
Persona.
Yeah. So in the chat, you should have the link to the live stream.
Very nice.
Great. So we're live. And welcome, Raiz, Paulina.
Thanks for putting this together again, Vasu.
No problem.
Thank you for having me as a spectator.
Yeah, well, feel free to chime in whenever you want to. So last time we were discussing Cauchy's integral formula, and we were trying to find some avatar of it in physics. And the route we took was the conformal Ward identities, seeing how they were almost a direct application of the integral formula. But it was a bit formalism heavy, and it's not by any means the nearest application of the integral formula or of the many interesting facets of analytic functions and their nice properties in physics. A lot of it is just present in more basic quantum field theory. But to get an appreciation of it, we need to build up some more tools. So today we'll start right from the propagator for a free field and build our way up to what's called the Callan-Lehmann spectral representation. And then appreciate the fact that it is a manifestation of what's called a dispersion relation that relates the real and imaginary part of an analytic, or really a meromorphic function, and see how we can derive it. So we'll kick things off with looking at the propagator for a free massive scalar field. So what it tells us is what is the quantum mechanical transition amplitude between for a field sourced at position x prime propagating to a sink at position x. And this sounds a bit strange or not, depending on what you're used to. But we'll bolster this intuition by looking at a whirl line representation for this quantity. For now, in terms of symbols, it looks as though it's an inverse of a differential operator. In particular, the differential operator is the D'Alembert operator plus the square of this quantity we call the mass.
Can you say a little bit about how physicists think about that quantity without it being a reciprocal? So the D'Alembert wave operator and this mass squared, if you acted on the state, what would a physicist expect?
So if you had a one particle state, right? So let's look at that more slowly. Free fields satisfy the following field equation. So if I take square sub x minus m squared, T1 phi. This is basically a wave equation for phi, because what it's saying is that I have, when I break it up into its various components, it's the sum of the squared partial derivatives in space minus the squared partial derivative in time. Right. And that there is a mass comes in the following way. Well, I'm not exactly sure about my conventions, but I think it's going to be a minus here. Phi equals 0, right? So that means this is a relativistic wave equation for phi. So phi is going to be composed of plane waves at the end of the day. And however, these are just, there's no polarization involved, so it's not like a light wave. These are just the sort of elementary building blocks of any other kind of wave phenomenon you're going to encounter. And this is just classical at this level, right? The fact that there's some field that satisfies this wave equation is a classical story. And how this quantity G comes up in classical physics is basically when you're solving not the homogeneous but the inhomogeneous wave equation. So say that I have to solve this equation, right? Where J is the source for the field phi. How I would do it is through the following algorithm. So I would just know that I can write the solution in this form, provided that the currently abstract quantity G satisfies this condition. So if G satisfies this equation, then you see that if I plug it back in here, I act with box minus m squared on phi, box minus m squared on G, because you see this is only acting on argument x, produces a delta function. I integrate with the delta function, I recover the source J.
Yeah.
Right. So this is a sort of basic intro to what it means to be a Green's function.
Right.
It's what lets you solve the inhomogeneous wave equation. And we'll see. Okay, so classically these are just two different equations, right? I mean, this is the homogeneous and inhomogeneous equations correspond to two different settings, really.
Systems, yeah.
Yeah, but we'll see why it's useful to interpolate between them in the quantum theory. In particular, the introduction of sources and then playing with what their values is, the fact that the source is given to you, and this is just the same as saying the source can be set to 0, right? Is very useful. Like that'll let you manipulate the path integral for this field theory later on. So this is the basic role of the quantity G, right? You could take it to be its defining characteristic. Right. So I've not kept conventions consistent here. There should be an overall minus sign, I guess. So never mind me.
Yeah, don't worry too much about that right this moment.
Yeah. So given that G satisfies the equation here, which allows it to be the thing that takes us from source to field, what we can then do is look at the defining quantity for the statistical field theory of a scalar field. Right. So now we started classical, and what we can do is move on to quantizing this theory. Right. So define a path integral, Euclidean path integral, with the following action. So the quantity up here is nothing but the classical action which reproduces the field equations that I was discussing before. So let me remove all but the exponent, and we'll meditate on that. So just to complete the story, if we perform arbitrary field variations of S, demand that those should be set to 0, we'll obtain the equations of motion.
Right.
From the quadratic nature of this function, you can almost immediately see that the equations of motion are going to be the inhomogeneous field equation that I wrote down before. Right. So square sub x, m squared equals j. And note that this is a function of j because I'm integrating over these fields phi. And as such, I can set j to be whatever I want. In particular, I can just set j to be 0. And I'll be using that freedom in what's to follow, in what follows. Also, because this is a quadratic function, what we can do is actually do the functional integral. You can actually perform the functional integral.
Mm-hmm.
You could treat this like a Gaussian integral, complete the square, and then do the phi integral. And what you'll find is that z of j is given by the following expression. Right. So what I wrote down here is the classical action that's valued in the fields and the sources. What we obtain by doing the path integral is a quantity called the effective action, which is basically the result of integrating over the, like integrating out all quantum fluctuations, if you would like. Mm-hmm. Right. So in some sense, you could treat W of J as a sort of classical object, roughly speaking. And from inspection, just by definition, W of J is going to be this double integral, right? X of G convolving both these J's at different points. Now, what is the idea here? The idea is that this quantity, thought of statistically, is the moment generating function, right, for this field theory. So this is some multivariate Gaussian integral, right? Basically, one Gaussian integral per point of space, if you'd like. And therefore, it's determined entirely by its covariance matrix, which is what G is. So that means any correlation function I'd want to compute comes from computing functional derivatives of log z, right? Connected correlation functions just comes from computing by doing repeated functional derivatives with respect to j. And because this was Gaussian, all correlation functions are just determined in terms of the 2-point correlation function. Right. Now, I should explain what this T is doing here. This T stands for time ordering. Mm-hmm. Right. It basically puts x to the future of y. And the reason why it appears here is that the path integral by default, like this quantity by default, time orders correlation functions. Mm-hmm. Its purpose is to compute time-ordered correlation functions through varying with respect to j. If you wanted any other kind of correlation function, you actually have to suit together different path integrals. You have to choose very weird time contours if you wanted to compute correlation functions, say at equal times or anything else. But we'll content ourselves with time-ordered correlation functions just because they carry the day as far as the calculations we do in perturbation theory and quantum field theory. They're all basically based on the time-ordered correlation functions and their relationship to scattering matrix elements, as seen through the lens of the LSZ reduction relations. But we'll get to that eventually. Let's just say that they're privileged for now. So at the object level, that's what G is. And here's its relation to Z, the generating function of free field correlators. Okay. And all this is doing is, glorified version of what's going on here, right? These correlation functions are basically telling you what's the amplitude to, source the field at x prime and propagate it to x. If you have higher point correlation functions, just have a bunch of hops that the field is doing. Yeah. So let's try and see if we can understand that from a sort of quantum mechanical perspective, which is what the Whirlwind formalism lets us do. Right. So there's some quantum mechanics behind this.
Very naively, when we do an asymptotic expansion of that exponential, we're like doing a combinatorial sum over every possible propagation, which is what we're about to see.
Yes, correct. So that is essentially what the Feynman diagram expansion should be seen as when we deal with it in an interacting quantum field theory. But before we can get to that, we need to understand where that intuition comes from. And that's through the Whirlwind representation. At least it's most directly seen through the Whirlwind representation. So it's just a sheer mathematical fact that you can write the inverse of this differential operator in terms of the following integral, right? So this is just a statement that the integral from 0 to infinity of dt e power minus t times f of anything you like is 1 over f. Right? So that's the basic identity that you're exploiting. And now if you wanted to sort of peel the layers of this onion, you go to momentum space, right? When you go to momentum space, you see that the quantity that you're playing with is nothing but the Hamiltonian of the free relativistic particle when you Wick rotate. So the Euclidean signature. And what you're doing is you're integrating over all time durations of e power minus ht, right? The sum over sort of propagation intervals is it goes hand in hand with the fact that this thing is kind of that in the quantum mechanical picture, you're trying to sum over all paths. In particular, you're trying to sum over all paths of whatever length, right? And so that's why there's this integral over dt here. And the net effect of summing over all paths, different paths really they only really differ by their proper length, which in terms is that's what this t really stands for. And that gives you the propagator. So that gives you the transition amplitude to go from x prime to x. And so that's what we have here. Right. So that's pretty neat. This is just a position space version of that.
Right. And I think this is like the clearest expression of what the propagator is so far. I mean, it's quite literally like the amplitude for time evolving the state from x prime to x.
Exactly. And it's really that you're just, these are just free relativistic particles. These are just free relativistic particles going from x prime to x. Now, what we can do is sharpen that intuition by seeing that it's really a quantum mechanical path integral with the whirlwind action here, right? Not the whole thing, just this transition amplitude is the quantum mechanical path integral for a free particle propagating from x prime to x in duration t.
Yeah.
The propagator itself is the integral over all these durations, all possible lengths of propagation. Now, what you can do is verify that these are the same thing by basically splitting up x into a classical piece and a fluctuation piece. Classical piece is just the straight line trajectory to go from x prime to x at a constant velocity with duration big T.
So this is making some kind of metric assumption, right? Like we're really like using flat space here.
Yeah, correct. Yeah, well, here already when I write this as x dot squared, I'm already in flat space. Yeah. So this is what and you're right, because this is what geodesics look like in flat space. And this is indeed a geodesic action.
Right.
So you have a classical geodesic plus fluctuations that are subject to Dirichlet boundary conditions. right? That's the idea. I fix the endpoints, and I know where I'm starting. I know where I'm going. I know that were there nothing quantum to happen, this particle is just going to fly in a straight line. That's just, Newton's first law, right? Now, computing this path integral now involves computing in the exponent what the action is going to be, and the action is just going to be this q dot squared piece. Knowing that there was a classical trajectory allows you to isolate this term. The effect of integrating over the fluctuations then, path integrating over the fluctuations, is giving you the following piece in the measure. Right? So it's giving you this 4 pi t to the minus d over 2. This is a Gaussian integral. And you just have to do this t integral, which you could either do directly or go to momentum space and notice that you just, recovered the momentum space propagator.
Right.
For the free field. So it's all consistent. This was just going in a little circle to make sure that the intuition that you're really quantizing the geodesic action is the right one. So in summary, the free field propagator comes from doing the whirl-line path integral, the path integral with the geodesic action for a relativistic particle on flat space, and integrating over all possible proper lengths of the geodesic.
Right.
And this is basically the underlying intuition that will generalize when you look at interacting field theories and Feynman diagrams. And further, even when you study string theory, right? And you do string perturbation theory. So this is sort of geometric backbone of everything that's to follow. So now we'll move on to what happens in an interacting scalar field theory. In particular, we'll see what happens to just the quadratic in source piece of the interacting field theory's generating function. Right, so we'll see what happens to the 2-point function. But before that, let's see what a dispersion relation is, because that's what we're aiming to uncover about this quantity. It's generally a relationship between the real and imaginary parts of some function, of some amplitude, or a vertex function. But yeah, it's a relationship between the real and imaginary parts, which tends to take the following form, right? Should this hold, that means you've uncovered a dispersion relation. Why it's called a dispersion relation? Yeah, why it's called a dispersion relation is because of some history to do with optics that I don't fully appreciate, apparently.
Not yet.
Yeah, not yet. Leave it in the comments if you know better. So now if you play a little bit with how you define the principal value, you'll see that you can take this relationship between the real and imaginary parts and turn it into a relationship between the entire function f and its imaginary part, right? So the use of relating the real and imaginary part is that you only really need to know the imaginary part in order to know the entire function. And that's the game. That's basically the game. There are instances where you can obtain the imaginary part of an amplitude, right? And that's really enough. That's all you need to reconstruct it. And this is certainly a property of a function that's meromorphic. It has to be analytic in most of the complex S plane. I haven't yet told you what S is. In most cases, it's some energy variable, so it's like a Mandelstam variable or something. But for now, you see that there's this complex S plane. Provided f is sufficiently well behaved, I should be able to do this contour integral and recover what f of s is, given that I know the imaginary part of f of s. So this is pretty cool. But say you're not given full knowledge of the imaginary part of FFS, right? Say you only know what it is. Sorry, just a second.
Busy Boston.
Yep. This is what happens when you live very close to the hospital. But
can you scroll up a
sure.
bit, possibly?
Yeah.
A little bit more. Yeah. Thank you.
Sure thing. So say you didn't know say you didn't know the imaginary part of F at large values of S. Right? So this is what happens in an effective field theory, say, where S is the center of mass energy, and you don't really know amplitudes at very high energy. What you then have to rely on is what's called a subtractor dispersion relation. So here, in order to know what happens at large S, I just really need to know what f of S prime is at very large S. You see, because the poles at S equals S prime. If I subtract, then I'm in a slightly better situation, because I can push my ignorance of what's going on at large S into an arbitrary constant of 0. I know that what I want is that F at large values of S vanishes in order for me to even be able to do a contour integral, right? The vanishing condition is basically the condition that lets me treat this quantity as capturing absorbing the sort of ignorance of what happens at high energies. And instead, what I say is I pick S, and then I do this, I look at the subtractor dispersion relation, where I have sort of a higher order pole, right? And I have now basically a handle on f of S given knowledge of this quantity even at lower energies. This sort of weights the low energy part of, or the low S part of the integral more heavily than the highest part of the integral. And that's very useful because it's exactly what you use in a lot of calculations in effective field theory. For our purposes, we'll use this trick to recover the spectral density from the propagator. That's what we're going for. But I haven't introduced the spectral density yet, so I will proceed to doing so.
It's the second time we're seeing this spectral representation.
Yeah, but we haven't. Yeah,
still remains a rather mysterious object and construction in my mind, even though we have some understanding of it now.
Yeah, no, I mean, it's I feel like I have a slightly better understanding of it now, but it is a rather magical thing. I mean, that it should be a neat, moderately well-behaved thing at all is surprising, and we should really comment on that, because these are things we take for granted. I mean, if you're a physicist, you're like, well, yeah, I mean, well, yeah, everything's analytic, right? Why wouldn't it be? But this is why we have you, right? Tells that we're actually in a rather special situation.
Rather special situation, indeed.
Yeah. So now let's look at the 2-point function in an interacting theory. I'll just give it another name. Instead of G, I'll call it gamma here. This is just because I wrote these notes in different times. In a weird order. Yeah, different times. Yeah. So I'll just jump into how you define the spectral density, or the Callan-Lehman spectral representation. You start by the trick of introducing a resolution of identity into this quantity, and then furthermore using Poincare invariance to put these field operators at the origin. Note that Poincare invariance here means that the vacuum is annihilated by the translation generators, and therefore the finite translation operator leaves the vacuum alone.
It just doesn't do anything. Yeah.
Exactly. And these ends are really momentum eigenstates. So that means that e power ipx is literally just e power ip sub nx.
Mhm.
That lets us write the 2-point function as the following quantity. This is basically the Fourier transformed sum over the squared transition amplitude between a one particle state and an n particle state.
Mhm.
The spectral density is basically the function that, well, it's basically this amplitude when you restrict to what's energetically allowable. You see, because of the conservation of energy momentum, to look at these transitions and have intermediate states be physical, be on shell, you really need to introduce these delta functions here.
Yeah.
So this is basically the sum of energetically allowed probabilities for a one particle state to transition into an n particle state.
Mhm.
Right.
All
So now,
possible such.
exactly, yeah. So now you plug this back into your expression for the 2-point function and see that there's an integral over mu squared, which is the argument of the spectral density that's introduced here. Furthermore, this delta function times step function defines the positive frequency part of the 2-point function of a free field. Right? So then you can just write the 2-point function as this weighted average over these positive frequency 2-point functions of a free field, right? And because of what we know about the relationship between delta functions and 1 over p squared minus mu squared, you see there's that principal value relation that we had here, right? So the delta function is just 1 over x minus x0 minus I epsilon minus 1 over x minus x0 plus I epsilon as you take epsilon to 0. Right? You basically see that the time-ordered product of the field functions, the g of xy that I was talking about before. So yeah, it's really not the same as gamma because gamma was just the Whiteman 2-point function, right? This is the sort of Feynman propagator.
Right.
Is still given by the weighted average over free field Feynman propagators with this quantity rho of mu squared, right? We knew at the word level what rho of mu squared is, the so-called spectral density. At the word level, it's the sum over energetically allowed transitions between a 1 and n particle state in the field theory, right? What we want is a definite sort of the way to compute it, right? We want to be able to compute it given the 2-point function. That's what we're building to. But for now,
let's be clear that it's rho times theta that's the sum over all of these
correct
transition amplitudes, and we're dropping theta in this expression. So
well, no. So the time ordering subsumes theta, right? So the Feynman propagator is time ordered, and the theta function that restricts to positive frequencies, Fourier transform, it's like the step function that keeps x to the future of y, and then so that's an important piece when you go from the
I see.
Yeah, I mean, at some point we could break that down, but I mean, you can probably see already.
No, I do see it.
Yeah. So now what's neat is let's plug this back into the world line representation so we get a feeling for why rho is called the spectral density. So we know how the free field propagator is written in terms of the world line geodesic path integral, right? And here you see it's just basically saying that you have an ensemble average over free field propagators with rho as a spectral density, right? What should you compare this to? Well, let's see. Compare this with how you write down the partition function in a statistical field theory in the microcanonical ensemble, right? So in the microcanonical ensemble, what you need to know is the density of states, right? That's what this rho of E is. And the energy spectrum, right? So let's write it like this.
Sum over state, like n particle states or energy states rather, and
exactly. So if this was literally just a discrete sum, I'm sorry, let's call it this. So I really mean sum over E. So it could even, this is really exactly. This could even be an integral because the energy levels might be so closely split that it might even be a continuous integral, right? So if I wanted to recover the fact that Z is also the sum over n of e power minus beta E sub n, then I just know that the spectral density, well, I shouldn't call it the spectral density, the density of states is just the sum of delta functions that set E to some E sub n. Right. So that means that my knowledge, you see, in the microcanonical ensemble, I just need to know what all the energies are, right? And I'm guaranteed that this will result in the following object, right? Which is the partition function. Trace of the exponential minus beta times h, right? That's the definition of the statistical partition function. What do I have here? Oh, it's not really the statistical partition function because this path integral has boundary conditions at x prime and x. However, sorry, this is not x prime and x. It should be x and y. That's my...
Your two states. It doesn't quite matter.
It doesn't quite matter, but let's just be consistent. Y, yeah, here we go. Yeah, now that's all good. So you see, if I instead, okay, what if I took periodic boundary conditions here? If I took periodic boundary conditions here, then I'd have e power minus beta h, right? And then I'm summing over time duration, which is just beta, which is the periodicity of the time circle. And this expression is just identical to this expression. So you see, rho of mu squared is the density of states for the Bose gas of relativistic free particles.
Right.
So it's playing the same role as this object here, which is just telling you where all the states are, right? So your knowledge of the spectrum of the theory is equivalent to your knowledge of rho. Right?
I mean, it's essentially the distribution over all energies, which might be extremely continuous in our setting.
Exactly. So I mean, this is just a sort of like idealized setting where you have all discrete energy levels and I can write it as the sum, right? Note that that's not what happens. Say, like, you know, if you have a conformal field theory in 2 dimensions, then this isn't what it actually looks like. What it really looks like is more weird exponential of the square root of energy. You have some cardi-like growth, say, at very high energies. That's what it looks like. Anyway, you see that, but you see the direct parallel between this spectral density and this density of states, right? So now it's clear that knowledge of rho is equivalent to knowledge of the spectrum of the theory, right? But if rho is a nice analytic function, then all we really need to know is knowledge of where the cuts and poles in the complex mu squared plane are, right? And that should be enough to recover rho. So the analytic structure of this quantity is dictated by the spectrum of the theory. In other words, by the spectrum of, by the cuts and branch cuts of rho. It's the poles and branch cuts, etc. of rho. And again, this is the thing that I'm taking lightly or taking for granted, which is that gamma of p is a neat analytic function.
Analytic, exactly. Yeah, which we have no justification for other than it helps.
At this point, that's all we really can say. So anyway, here's what the 2-point function singularity structure looks like if you have an interacting theory. If you have a free theory, there's just a pole at some value of p squared, right?
Minimal.
P squared equals n squared.
Right.
If it's interacting, then there's also a branch cut, right? Branch cut starting at the threshold for particle production, right? So that's the structure that I'm writing down here.
Yeah.
Now the spectral density, so knowing this is equivalent to knowing what the spectral density is doing, because the free field propagator always has this structure, right? So if all I need is knowledge of the free field propagator plus the spectral density to know what's happening with the 2-point function of the interacting theory, right? So the spectral density has this profile for free theory, right? All it's doing is it's saying that p squared has to be m squared. In other words, it's like saying that you had just one energy in this kind of sum.
Right. Right.
But in an interacting theory, it's got this additional interesting part, right? It has this sort of delta function, and then it has this additional part that accounts for the deviation from the simple free field structure.
Right.
Nonetheless, it's as though you were doing an ensemble average here, right? So it still is just telling you, however close the different masses are, it's still just telling you how your excitations are distributed in energy space.
Right.
Right. So now what we want to do is recover rho of p squared from knowing gamma of p squared. Why? Because through perturbation theory, what you can compute is gamma of p squared. Okay, so that's what you have access to. But what you want to know is this, obviously. This is way more interesting, right? It's telling you something about the entire spectrum of the theory. If there was a way for you to just get a hold of this guy, which if you think about it is a pretty low bar, you know, like
it's just a 2-point function. Yeah.
Exactly. It's just a 2-point function. But if you could determine that quantity non-perturbatively, you actually have access to the entire spectrum. Just pretty cool, right? Now, to determine, you know, so if you were handed this function, if you were to do the experiments to compute these transition amplitudes somehow, that means you have knowledge of this object. How would you recover the spectral density? And the answer is by being clever and using Cauchy's theorem, right? So we'll go back to our exercise of writing f of p squared if f is an analytic function with just a simple pole in the following way. Right? So we need this contour not to cross any singularities. And we know that this is what it looks like for an interacting theory. How do we know? You do some perturbative calculations in how many ever free field theories you like. This is by and large what the structure looks like. And what you want to do,
like until you're convinced.
Yeah. And what you want to do is not keep this Pac-Man contour, but blow it up, take R to infinity.
Right.
Why you want to do that is because the spectral density is given by an integral over S from 0 to infinity, right? You want this to sort of stretch out. But in order to do this well, you need to be able to account for ultraviolet divergences, right? Because this is the energy plane.
Behavior at large energy, to put it in more pedestrian terms.
Yeah, exactly. So as we discussed,
like what poles exist at very large energy.
Yeah, so what you want to do is more like just by default, you know, allow yourself to do this contour integral by assuming that this is a well-behaved function at large energies, in particular, and absorb
vanishing, right?
Exactly. And demand that it's vanishing by pushing your ignorance into gamma of p naught squared, the subtraction constant. And instead of computing the contour integral at first order pole, do it at a second order pole.
I now understand this argument a whole lot better. I love that you've presented it this way. So I mean, this P0 is essentially like you're subtracting off like the high energy content, right?
Precisely.
You're assuming that it doesn't diverge, in particular that it doesn't blow up to infinity, so that you can just kill the high energy behavior and you reset the high energy behavior to 0, and it allows you to get this kind of expansion.
Exactly. And that's essentially the same set of steps as what you would be doing in conventional renormalization.
Yeah. Which, I mean, except like maybe there you might also subtract off like an actual polar part. Like if there is a, if there is actually some meromorphicity, then you might also like kill the polar part with your meromorphic expansion. And here we're not doing that. We're only killing the zeroth order part.
Exactly. Very good. But another virtue of doing this is now you can sort of expand out your contour without qualms and keep this polynomial of p squared that accounts for the very high energy behavior. So the cost of sending R to infinity is this polynomial of p squared, which is this gamma of p squared. And so we know that the 2-point function sees a pole and a branch cut, right? Which means that if I wanted to send this contour, like if I wanted to blow up that Pac-Man, and I wanted to get this contour to lie along the real s-axis, I have to be able to compute the discontinuity of gamma, right? Which in turn, because of the Schwartz reflection property, is that what it's called? The property that if you have a real, if it's real along if the function's real along the real axis, then, and it's analytic, that means that anywhere else it should satisfy f of s equals f star of s star, right? The discontinuity in the 2-point function is just given by 2i or minus half I times the imaginary part.
Proportional to this imaginary part,
Exactly. And this is a dispersion relation, right? And now notice that this integral has exactly the structure that you need to read off the spectral density. So the spectral density is actually determined by the imaginary part of this transition amplitude.
So this is a really marvelous relation. I mean, this is like a really strong constraint on the 2-point functions of any unitary quantum field theory. Effectively telling you that the energy spectrum is encoded in like the imaginary strip.
Right, which you would not expect.
One cannot emphasize how deep this fact is. This is a crazy, crazy fact. I mean, that maybe number theorists even observed a long time ago by studying the Riemann zeta function, where there too, the behavior of the whole Riemann zeta function is determined by like the poles and zeros along like an imaginary strip, like a vertical imaginary strip. So
that is fascinating. It would be nice to it'd be nice to see
that.
But nevertheless, you see that the crucial role here is being played by your ability to say something like this,
which comes down to analyticity.
Analyticity of a transition amplitude, right? Which is a very fascinating thing, because what have we done really? We have analytically continued energy, center of mass energy, into the complex plane, right? And we're looking at the imaginary part of the amplitude as a function of complexified energy, which sounds ridiculous. There should be nothing physical about this, but in fact, there's something entirely physical about this. In some sense, all the physics about the spectrum lies just in this, right?
Right.
Like the quantum mechanics behind any quantum field theory is just the spectrum of the theory, essentially, right? In some sense, there's knowing just the Hamiltonian is like knowing the spectrum, just the quantum mechanics, exactly. And that all lies in the imaginary part of the 2-point function, or basically
function,
as a function of complex energies, right? It's analytic structure in the complex energy plane. So it's like, this is just to say that when we would say that complexifying energy sounds like an entirely unphysical thing to do, we're being very short-sighted, right? If that was our position, right? It seems like you can extract something deeply physical by going to the complex energy plane and then demanding analyticity.
So basically asking that our 2-point function extends off the real energy locus into some complex variable, we pick up some kind of symmetry in the whole quantum field theory. It's like there's information encoded off the purely real locus
Exactly.
that
Exactly.
you can access just by demanding that gamma is analytic or like holomorphic.
Absolutely, yeah.
And,
Which is so bizarre.
maybe it's worth saying that for a sufficiently well-behaved real analytic function, so defined on the real axis, we can ask, does it extend analytically or holomorphically into the complex plane? And we have some simple criterion for when that's possible. It's just the existence of sufficiently many derivatives in a small neighborhood of any point. And then you get this, how to say, analytic continuation principle.
Right.
As long as arbitrary derivatives of arbitrary order exist, then we can actually naturally just extend such a function. So maybe another way to look at it is not that we're constraining the function, but that there is a natural extension of the function into complex energies that just comes for free. It comes by the nature of reality, so to speak. And here we're not even talking about like physical reality necessarily.
Sure, but this is actually very interesting because you see, naively, you have the structure of an analytic function, so some kind of rational function, right? That's what this looks like. But we go all the way back here. The reason why we have analyticity, the ability to analytically continue, is because this is some simple rational function when you invert it in momentum space. Right. It just came from, the wave operator.
Yeah.
Right. And the fact is that when you go through the song and dance and realize that an interacting theory has as its 2-point function just a weighted average over free field 2-point functions with some sufficiently well-behaved row of mu squared, then you just have another rational function, and it's very believable that thing should have a nice Taylor series, Taylor expansion, so that you can analytically continue it. And that is very neat, right? That's like, it's like really interesting and powerful thing.
This kind of technique of taking like a 2-point correlator, say in a conformal field theory, is it just a standard calculation to extract the energy density?
That's a good question. So, okay, when you do this in a conformal field theory, you're relying on something slightly different, I would say. So,
2-point correlators are slightly different, right?
Well, so in a conformal field theory,
or even let's talk about like the chiral halves of 2-point correlators. So I just mean like,
sure. So I guess if you're in a conformal field theory in 2 dimensions, what you realize is that the spectrum of anomalous dimensions on the plane maps to the spectrum of energy levels on the cylinder because of the state operator map that we discussed. And so there, when you actually, we could do run the whole gamut, right?
Look at it right now.
Yeah. So you see, you have, for sort of sufficiently well-behaved unitary conformal field theory. So let's go down to 2 dimensions, just because that's where you pose the question. If these are primaries, then you know that this is going to be the following object. So what we have here is a delta function that sets O1 and O2 to be the same operator, and the exponent here to be 2 delta. By Z1, I really mean Z1, bar Z1. Right? If I want the modulus there. Otherwise, this would just be the chiral part.
Right.
Now, the interesting thing is that in the state operator map, what I have, because okay, E1 or E2 are the same because of this delta 1, 2, or delta 2, 1, whatever you want to call it. I have that the energy of this state is directly related to the conformal weight. So R is the radius of the spatial circle, right?
Mm-hmm.
And C is the central charge of the theory.
Mm-hmm.
So the effect of inserting O1 at the origin on the plane is to generate a state on the cylinder that has energy E1.
Mm-hmm.
That's how the state operator map works. Now, what is the bookkeeping device that knows, okay, what's the analog of our friend here, right? When we write it in the Wordline formalism, we have this jazz, right? And that is going to be the partition function, right? It's going to be trace, or sum over n e power minus beta e sub n, right? And in a conformal field theory, this is just going to be the following product of pure numbers. So minus here. There's some pi's that I'm missing, but that's is basically the analog of that propagator with the boundary conditions taken to be at the same point.
Right.
Right. And as we discussed, you can write this as integral dE rho of E and this is exactly the same thing as what we discussed before, but notice that because these are really simply related, you now have a I'll call this bar beta because it's basically beta over R.
Right.
All sort of dimensionless quantities. But the spectral density is now a density in the space of conformal weights.
Mm-hmm.
It's dictating what the weights are going to be like. And so the energy spectrum on the cylinder, this is technically the partition function for the theory on a torus because you've taken time to be periodic. If you took it on the cylinder, then you'd have the analog of those boundary conditions I wrote above.
Mm-hmm. Mm-hmm.
Nevertheless, the sum over these levels is just going to be, so the sum of the density of these energy levels is just going to be a density of these weights. You see?
Yeah.
So the energy spectrum, the spectral density determines the spectrum of these anomalous dimensions.
Right. Which
so that's
we can
the, yeah.
We can express the actual energy levels in terms of these anomalous dimensions, but the true quantity in these CFTs is actually these anomalous dimensions. Mm.
Yeah, yeah. And that's the best way to organize a spectrum.
Mm.
But you see there's a direct relation again between the 2-point function and this quantity.
Yeah, absolutely. Mm. I certainly found this extremely useful to see it again from a slightly changed point of view. I think the chief question I had from the last time has actually been answered, which is what exactly we were doing with this energy shift in energy space from like, or rather in momentum space from, subtracting off the P0 part.
Mm-hmm, mm-hmm.
That part is completely answered in my mind now.
That's great. Well, we didn't quite record that discussion, did we? The one where we were actually considering what was happening with the subtractor dispersion relations and such.
I'm not sure. I mean, I'm not sure how much of this we recorded at all, I
That's
guess.
true. Oh, this is being.
The last from the last session, I mean. I'm not sure if we
I see,
recorded
I
that at
see.
all, right? No.
Yeah, me neither. Me neither. But yeah, basically it's just a matter of weighting the high energy and low energy parts of this integral.
Yeah. So
Yeah.
I suppose another naive question I have from all of this is that we know how to take a free theory and
Mhm.
we understand the role the propagator plays and the relationship to the, or let me say it differently. Rather, in an interacting theory, we know how to take the 2-point correlator and relate it to propagators for a free field theory. But
Mhm.
do we have any interpretation of any relationship between the propagator for the non-free theory and the 2-point function for the non-free theory?
Oh well, those are still the same thing, right? I mean, you still interpret that to be the amplitude to go from. Well, okay, let's
Yeah,
put it this way.
it's got the absolutely naive interpretation where, I mean, it is literally just another representation of the propagator, right?
Yeah.
It's the same information, but I suppose I'm
Right.
asking something slightly different. But go on.
I mean, are you asking what the analog of this condition is?
Yes,
So the analog of this condition is
that is exactly what I'm
basically.
asking.
Okay, good.
Because now we have to introduce some kind of potential to perturb
Exactly.
our inverse operator, or here you're just writing it.
This
So
is still true.
we'll get an interacting Green's function. And then my question is roughly, can we, at the level of Green's functions, can we relate the free Green's function?
Correct, we can. It's exactly what you do.
Mm.
There's a Feynman diagram expansion for it.
Right, right.
As you can imagine, it's sensitive to the form of V,
Mm-hmm.
right? So basically, you can
Because
write.
all of our
Yeah,
exponentials had these operators in them, right? So we're basically just perturbing those exponentials and trying to get some kind of asymptotic expansion.
yeah. So basically, there's going to be some kind of the very basic form of it is sum over n. Let's put it this way: c sub n of p squared lambda power n, where lambda is a coupling constant. You just have some kind of power series to define this. And you can compute this order by order in perturbation theory. So in fact, you could take this to be like n greater than 0 plus gxy. And this is what you need Feynman diagrams to compute these terms. So basically you have.
Yeah, this is exactly what I was asking for.
Yeah. Because note that this is really a function of lambda.
Mm-hmm.
Now, to actually compute this series from here is Schwinger-Dyson. You're using the Schwinger-Dyson equations. Tends to not be the easiest thing to do, or it's not the textbook thing to do. The textbook thing to do is just develop Feynman rules and then compute a series of corrections here. Well, sorry, this should be p squared because I'm doing everything
in momentum
space.
Yeah.
There's presumably some cutoff dependence here too. But, yeah, whatever. So this is basically the idea.
Yeah. No, I'm quite satisfied.
Yeah.
And so at the end of the day, knowing an interactive theory can really reduce down to these coefficients, these CNs.
Yeah, so that's another interesting discussion to have, because you could say that that's definitely the case for a theory at weakly coupled theory. Now, more generally, what is the meaning of this series, right? This is just some asymptotic expansion. Particularly, this doesn't actually do justice to the kinds of corrections you can compute here. Really, you should know, like knowing everything means you know what happens to corrections of the form right? This here, etc. So you have something like this, and so on. This in particular is an instanton type correction, which is some non-perturbative effect. So the philosophy that states that the most generalized kind of expansion that I can think of here is some kind of resurgent trans series, and that is all we really need to define an interacting quantum field theory. This is the idea of resurgence and resummation.
No, that's a rather beautiful way to arrive at it.
And in some sense, it is your default position if you're a physicist. That's your default position about how to define quantum field theory, whether you know it or not. Alternatively, you say, "Oh, I put everything on a lattice and I do this and that." But if you were to translate all that into some formal power series, it's going to have some structure, and the structure is going to be the simple series plus corrections that involve quantities like this. These are instantons. You could have something more complicated called renormalons, and yeah, what exactly, where do they appear, etc. This is all active research. People don't really know.
Right. I mean, we're basically just trying to classify different kinds of perturbations that to the free structure that we can actually reason about using whatever mathematical techniques are available to us.
Exactly. And in fact, this is gonna basically correspond to perturbations not just around free structure, but you just have different, say you'd have different saddles, or you have different classical solutions, and you have expansions around them. You need to consider all possible such saddles. That means that in principle, you have some other index here, and you have the sum over n and k. Just, yeah, you have to run the gamut. It's very interesting field.
Oh, I love this. I love that we have ended at this. This is another, I would say, from a practicing QFT point of view, this is like absolutely bread and butter. It's like you can't even begin to like approach calculating anything if you're not aware of this kind of structure.
Exactly. I mean, which in some sense, what are you aiming for? Right?
Exactly. Yeah.
So you're basically aiming for being able to do stuff like this. We'll call these coefficients D. This is all just symbolic, shouldn't be taken too seriously, but you get the basic idea.
Yeah.
These things like this. Yeah.
Yeah, so maybe this begs the question. I mean, I think there are multiple directions we can go from here. I mean, I'm really glad we have this material down. I mean, we could approach, I mean, all of this is done in a slightly abstract point of view, in the sense that we're reasoning about things that apply to many quantum field theories. We could go in a number of different directions. We could try to specialize and compute some very concrete quantities in some really basic examples with concrete interaction potentials. We could go in a completely different direction. I mean, we had this goal of like approaching reggae theory, really understanding these leading and subleading pole corrections, and we now have like a good proportion of the language to even attempt to do that.
Right. So we could generalize in two ways. We could continue our discussion of say dispersion relations, analytic properties of different, like now, like more complicated amplitudes. Instead of just having the propagation amplitude, you have like the 2-to-2 scattering amplitude.
Right.
And that'll lead us all the way to like Regé poles and everything else in the dual resonance model. Or we could, as you said, do something more pedagogical, look at something concrete, and do the necessary calculation. For instance, you see that actually the spectral representation comes in to master normalization in an interesting way. And we could just compute that to leading order and perturbation theory in some simple theory. That's another way to go. And we could also discuss the heat kernel. In fact, we could do all of these.
Why don't we do the heat kernel next? Like actually treat like heat diffusion on Feynman digraphs embedded in space-time and try to do justice to that perspective.
Yeah, we could do that.
I think that's even my whole basis of like what Feynman diagrams mean in my present understanding of quantum field theory.
For sure. So we're just going to be generalizing this picture, introducing. Yeah, we could do that.
Let's do that.
I'm happy with that. Yeah.
You want to aim for like, we don't have to wait for the weekend. We can try and do that on Thursday.
Try with a capital T. I'm not exactly sure.
Try with a capital T. Yeah, I mean, no pressure, but we could just say in a couple days, Wednesday, Thursday, we can try and do another session just like this, and we can do.
I'm happy to, because the thing is that the heat kernel exposes a lot of the anatomy of quantum field theory. In some sense, we can sort of see how the vacuum energy can be computed from a whirl-line perspective, right? We can also see what the effective regularization is at the level of the whirl-line itself.
Yeah,
right? The whirl-line integrals.
And we should do both of those.
I feel like the heat kernel opens the door to all of that.
Yeah.
So let's do heat kernel next.
And I could even I don't know how ambitious this is, but there's a heat kernel representation for the chiral blocks of the Kac-Moody vertex algebra.
That's nice. I want to see that.
Which I've worked through only once before, and I could prepare a section. It's actually pretty hardcore math. But I can do my best to make it presentable. You essentially reduce like solving the Knežević-Zanolodchikov-Bernard equations, which you think of as maybe something is intrinsically two-dimensional, like belonging to 2D conformal field theory. And through a series of pretty clever manipulations with differential operators, you can reduce it to a one-dimensional problem involving a heat kernel.
Nice.
It's very explicit, all of it can be done quite concretely, but making sense of what it means exactly is something I've been wanting to do for a while. So how about I can prepare that as the more advanced segment of what we can start as much more elementary in terms of heat diffusion on these graphs.
Awesome. No, that sounds good. Sounds good to me. I'm down.
Okay. So maybe we'll break here, and then in a couple days,
let's break here.
We'll pick up.
Awesome. Okay. Well, thank you all for your attention.